Okay, all right. So I will start with my brief introduction first. So my name is Abhay Dutt Paroha. I'm working as a software team leader with Schlumberger. Short name is SLB. And today's topic is scaling oil field production operation using cloud computing. So I completely agree with the last presenter, and he focuses on uh, the requirement and keep it simple. So yeah, that is also I follow in day-to-day life. I mean, I usually build solutions incrementally, not everything on single day. I mean, I start with something small, then keep iterating over it. So yeah, I completely agree with whatever he presented. Okay, so before going into the main topic, I would like to give a brief introduction about oil and gas business. So, for the folks who don't know, so Schlumberger is world's number one company in upstream oil and gas services. So, around the globe, there are mainly two kind of companies dealing with oil and gas business. The first part of company are basically oil and gas company who basically owns the oil well, and these oil wells could be anywhere on earth or in offshore in middle of the sea. And second of the company which are basically operating in these oil and gas wells. So I'm from the second part. I'm working for the service provider. So Schlumberger is a world's number one service provider, and what we do, we basically deals with upstream. So if you want to know what is upstream, so I'm showing on the screen. So the left hand side that call upstream, the middle says midstream, and the right one says downstream. So what we do basically, so we basically involved in everything, whatever involves in drilling the oil well and extracting the oil from under the earth. And this oil well, as I said, it could be a middle of the sea, it could be on some desert or some remote area. So everything involved, including some tools and technologies and hardware and software, everything. So we provide all kind of technologies. And when I'm saying skill set, you will find petroleum engineers or geophysicists or petrophysicists, geologists, and software engineers, data scientists, machine learning engineers. So everyone working as a team, and our single goal is to optimize the oil production. So we want to apply all technologies together so that we can optimize the oil production. And as you can see on left hand side, I'm showing two pictures. One is the onshore pump jack. You will mostly see that rod is basically going up and down. It is basically drilling the oil well. And the other picture says, okay, someone using some helicopter and landing on that a bad location where there is some instruments are installed in middle of the sea, and they are basically producing the oil. And there are midstream companies. These companies are basically responsible for processing and storage. I mean, once the oil is produced, then someone should be there to transfer it. So these companies are mostly build the pipelines and transport and trucks. And the third kind of companies are downstream companies. So once this oil is already reached to the distribution center, so these companies are basically refining the oil, and after that they also deal with the sales and marketing. So today's topic is mostly on upstream, and about a cloud-based solution what we built, and it basically helped to optimize oil production. So I would like to start with some terms like what is a digital oil field. So digital oil field is just a fancy name what we use. I mean, it's nothing new. It's there in the industry since last more than 25 years. But since last more than 10 years, everyone started talking about a cloud, and now we have chat GPT and machine learning and data scientists. So digital term, I mean, people started correlating it with the cloud and machine learning and everything. But for us, the digital oil field is anything related to computer. So digital oil field, I mean, even before the cloud computing, it was there. But now we are using it more proactively, and it is related to using any digital technologies. It could be software or hardware or data analytics, and the end goal is to enhance the exploration, production, and management of these oil gas field. And the general operation involved, I mean, if we are collecting a lot of data from the sensors installed in this oil field, so basically artificial intelligence is involved and internet of things are also involved. So as you can see, the right hand picture I generated from AI. So this picture is basically showing a typical oil field where several people are working, and you can also see some hardware are installed, some computer screens are installed. They connect it to some satellite so that they can get the internet connection and everything, and they're always sending some data to the remote oil field operation. So today's topic is about the similar application which is installed and which is basically optimizing this digital oil field operation. So I would like to start with the challenges, the requirement, what we learned in the last session as well. So the challenges and requirement for production operation means because this operation is highly complex, it basically involves a lot many people from different business roles and from different geographies, and different workflows are always applied. So these problems are typically solved using a diverse or disconnected set of software application and tools. And before introducing the cloud computing part, we were still doing this operation, but at less scale. And so the main challenge for with the application, the existing application was, I mean, the collection of data was not easy, and to make this data available for running a scalable workflow, that was not straightforward, because our data was scattered and there was so many on-prem uh, desktop based application was running and collecting, so it was not very much scalable. Second thing was in oil field, the data frequency could be very different. Few data could be second best data or maybe less than second best data. Few data could be monthly, yearly, weekly, or daily. And there are several conventions followed by different oil companies around the globe. So whenever we have some existing desktop based applications, then each application talks their own data standard. So whenever we are transferring data from one app to other, we always need to build some kind of connectors or adapters so that one application understand what the other application is talking about. And it was very hard to maintain, it was not very much easily accessible, and poor scalability, and it was leading to non-productive time and data quality issue as well. And at the end, it was giving some inconsistencies as well, because in this on-prem app, I mean, if there's a data became inconsistent, then I need to import that data again and connect it to the several application a couple of times. So that was not a good way to run these workflows. And other common complaint from customer was they always see a missing data or incomplete data. So they were missing a complete and consistent view of data always. So these are the challenge. So okay, I talked enough about data, about frequencies and all, but I would like to give some context. How does that data look like? So on very high level, I would like to split the data into the uh, two kind of data. I mean, one is the time series data, other one is the structural data. When I'm saying time series data, so whenever we are drilling the oil well and we are putting a lot many tools inside the earth, so with that drilling pipeline there are a lot many sensors installed, and these sensors are basically capturing a lot of data points from beneath the earth. These data points could be, in simple terms, a pressure or temperature or the gas flow rate or oil flow rate or water flow rate. And typically, this time series data looks like what I'm showing on the right hand side. The first one is, say, okay, there is an acquisition time which is associated with every data point. Let's say I'm showing that some value, let's say some oil production volume coming. So I'm showing 2.3. I'm assigning the unit of measurement as well, and I'm also assigning the kind of data. Is it double or string, so that my storage system or my workflows also understand it. I'm also assigning the source acquisition time. I mean, okay, Source acquisition time means when I really see the data on my cloud. So agent acquisition time means the acquisition time when the on-prem tool, which is basically streaming that data point, and the source acquisition when I start seeing that data point on cloud. So there are typical key characteristic for this time series data, which is important for our workflows. So for example, let's say if I want to see a forecast of the oil production. So I'm basically interested in the trends and pattern because I want to apply the time series analysis, which is basically a typical machine learning workflow. So it is only possible if your data is stored as in a time series manner. So time series means it always has some temporality associated with it. I mean, it's chronological order maintained. Then this data could be a periodic or sporadic. Periodic means when we have some defined frequency like daily, hourly, or minute based, or there are possible that there are some sporadic operation. For example, if there is some downtime activity in certain well, so this downtime activity is like a sporadic event. I mean, there is no fixed interval associated with it. The downtime started may now, it may finish maybe in an hour, or it may go for more than an hour also. Third type is why we want to see the time series data, because it has some pattern associated with it, and we our workflows want to analyze these pattern. And there is always a seasonality associated with time series data, which involves pattern that repeat at the known interval. It could be daily, weekly, or yearly. So second type of data is basically structural data. So to explain this data, I would like to give you one example. Let's say if some oil and gas company has some oil well, let's say in the Texas. In Texas, there is one city, Cameron. So you can think of it's like, okay, maybe in North America, that oil and gas company may have different oil wells in different geographical location. So they always start with the top route, that is basically a country. Then they will go to the state, or they may create a zone area as well. I mean, they can combine multiple geography. They can start calling it as a zone, and after that, they are basically reaching towards the geography where oil well is actually located. So they always identify it using latitude and longitude of oil well. So on the right hand side, I'm basically showing this kind of data, which is structural data. As you can see, this is a graph based structure. So on the center, you see a well is located, and there are three kind of branches coming out from that well. One is in orange color, one is in red color, yellow, and green. So these different branches are basically showing hierarchies where this well is attached. So well is obviously attached to some field where we are basically doing the drilling operation. That field is as exist in some state. So that's why that one line shows, okay, this oil well exists in this state. Then there is another hierarchy which is basically for petroleum engineers. If they want to know the reservoir and zone and completion. So completion is another concept. It is basically an area under the oil well from where oil actually produced. So that area is basically called completion. Then I'm showing other hierarchy as well. For example, if there are tools installed, so whenever oil is coming on the earth surface, then there are multiple tools installed. We call it pump and flow lines and separators. So that hierarchy basically shows, okay, this oil well tools are basically connected to these subsurface components on the earth. Then there are other hierarchy like events. As I said, if there's a downtime event or something else, they have their own hierarchy. So, and this structure is basically a graph based structure. So you can see what we want to store. Okay, the node ID itself, and the edges, and the started and ended. So all these entities in this system are connected by several hierarchies. And as I said, okay, the same entity could be attached to the multiple hierarchy as well. So the main challenge is, now we talked about the data, the time series data, and the structural data. So time series data could be very huge. It could be a petabytes of data for more than 10 years or so. And for structural, it is basically a graphical data. So our challenge is to create a scalable cloud storage so that we can store this massive data and this graph structural data. So how did we solve this? So our first problem was the data ingestion problem. So in the production operation, as I said, there are several sensors installed and there are several tools installed, and we have different kind of data sources as well. So there are typical data source, like if there is an on-prem or relational database, that's called a production data management solution. There could be edge-based or IoT-based devices streaming data. There are mobile phone as well. I mean, someone is just capturing some data and preparing some report. There could be a physics-based model. If you guys don't know about the physics-based model, so for example, in any oil field, they install multi-phase flow meter. So the job of this multi-phase flow meter is like to check the liquid liquid characteristic and the heat exchange rate, and what is the characteristic of the oil, gas, and water proportion whenever that raw oil coming from the earth. So we want to capture a different kind of data from the different kind of sources. So we definitely need a scalable data ingestion system, and data is really important because 80% of the time any production engineer or petroleum engineer, they always keep looking at data because their workflows are basically data intensive. So to solve this problem, what we did, we created autonomous agents. So autonomous agent is a very famous term these days. We use it for creating machine learning models and LLM model also. But yeah, autonomous agent means any software process which is running continuously and acting on the events it received. So for us, we always want, okay, some process to run closer to the data source and keep listening for the events, like if some new data point arrived, or if you want to fetch the data for more than 20 years, because there are few wells who are producing oil since last more than 100 years as well. So we want to fetch all this 100 years of data, and you can just imagine the scale. If some well producing a second base frequency data for 100 years, there could be billions of data points. So we want to push all these data points to our cloud storage. So we produce this agent. These agents, in simple term, you can think of it's like a Windows service running continuously. And whenever it receives some event from the on-prem data source, it is pushing those data points securely to the cloud storage. So each agent is basically uh, associated with a unique agent ID, what we handle on cloud. And for security, if you want to secure the communication channel between the on-prem and cloud, so we use a cloud-based service account, so that whenever someone is installing those agent, that person is always using the encryption key coming from the cloud-based service account. Then that installer is basically decrypt that key, and after that we don't have any idea about that key because we are not storing anything. And whenever I'm communicating from on-prem to cloud using some messaging queue, that channel is also encrypted using same key. So it makes sure that we are not spoofing anything, and each agent is basically talking to the same messaging topic associated with its cloud service account. So this is for handling the data ingestion. So in this slide, I'm basically showing the typical life cycle of any agent. And right hand side, I'm also showing one picture. So this picture is basically from the patent I filed. So this patent is already approved. So this is for showing the life cycle of the agent. So this basically shows any agent can send the time series and structural data, what I showed earlier. We are using the protobuf, the Google protobuf for format for serializing and deserializing. We can always send the incremental data on daily basis or hourly basis or second base or historical. And this agent can also request some configuration at the startup on periodically or demand from cloud. And it always use some messaging or communication mechanism so that it can scale really well. It can also receive some commands from cloud. Okay, let's say someone wants to fetch the last 80 years of data, then that person can basically use some APIs hosted on cloud, and it can start those jobs manually. And other challenge what we solve, okay, we need something to monitor, so we are using the same uh, messaging pub sub communication mechanism to send the logging and monitoring status as well. Those we call heartbeat, and we are monitoring those heartbeats on cloud. So we basically created some dashboard so that we always see, okay, our agent is up or not. Now, moving over to the agent lifecycle, the typical agent lifecycle start if someone register that agent on cloud, you using some set of API. So when agent is registered on cloud, then we basically associate it with some cloud service account. So we maintain the authentication and authorization part. And that cloud service account is also associated with some cloud PubSub mechanism. So when I'm saying cloud PubSub mechanism, so in Google Cloud, it's a cloud PubSub, or in Azure, it is Azure Service Bus, and for AWS, it is SNS or SQS. And agent installation, like after registering the agent, I want to install it on the on-prem machine so that it is always attached to that particular data source. So I use the same cloud service account key, and after completing the installation, if it is a Windows server, it basically encrypts it using the Windows Data Protection API. So as soon as agent is started, it basically starts streaming data on cloud. Then the ingestion part, it is basically sending the oil production data from these oil fields, and data is pushed using the same messaging, any PubSub mechanism. And yeah, we also can send commands from cloud to on-prem for if we want to fetch any historical data. So one important point was, let's say if there is a some disaster happens on cloud, okay, so what is the best way to reduce the downtime, because I don't want our customer to wait. So in disaster scenario, the strategy we followed, we created a global cloud resource which is available in multi-zone. So whenever and also because we were using the cloud PubSub, so by default cloud PubSub has the message storage for more than 7 days. So, so even if some service is not available, some disaster happen on cloud side, so that message is still present in that queue for at least 7 days. And by creating a global resource, that project is global, so it is available in the multiple cloud zone. So we can easily recover that disaster scenarios, and we can replay all those messages which are in the queue for last 7 days. So it basically help us to achieve the disaster mechanism for solving the ingestion problem. Now I want to store, okay, now data is arrived. I want to store that data on cloud. So the main challenge in any oil production operation is, okay, everyone start using their own terminology, own data model. So someone wants to call something like area, field, station, or well. Other person wants to call it some other tank and compressor. So there are several domain concepts like field, asset, surface, subsurface, equipment, well, boreholes, and completion. Our goal is to present every single thing by using these three terms only. One is called entities, second is called properties, and third one is called the relationships. So entity is like anything. It could be well or completion or any tool or compressor. Our properties could be any data coming from that particular entity. It could be pressure, temperature, or oil flow rate. And relationships is like how these hierarchies are attached to each other. So we basically created a canonical domain model so that we can represent every single thing by using a common terms. And it will solve the problem what we faced earlier when every single application was using their own data model. And we are always solving this problem again and again. So another use case, just to explain you why we need a canonical data model. Let's say in there some field, there are two sensors installed. One is streaming, and both are streaming frequency. One is coming from the IoT source. The second one is coming from some database. let's say one person calling is IoT source like ESP dot frequency in hertz, and second person is calling just like ESP underscore frequency in hertz. But for our production domain model, it is just ESP frequency. We don't care about how the main data source want to name it or tag it. Whenever data is coming to our data storage, we want to apply our own domain model concept. So it basically help us to resolve the different terminology and data standard, because now we understand, okay, we are talking a same language and we are not confused about what other people are giving some other tag or name. So other challenge was, okay, we wanted to store this huge amounts of time series data and structural data, and our main requirement was we always want to keep the history of data, because let's say if I'm running a forecasting operation or I'm running some other recommendation engine workflow, I wanted to see the history of data always. I don't want to delete anything. I always want to append everything. So we solve this problem using bitemporal storage. So bitemporality is a concept when we assign at least two timestamp. One is like a valid time. Second one is called the transaction time. So valid time is like the actual time when that physical measurement happened at the source, like when we measure the pressure at source. And transaction time is when I basically storing that data into our cloud storage. So it basically helped us by storing these two timestamp. It helped us to run the temporal queries. It is very useful for running any kind of historical analysis. It also help us to achieve the temporal trends and running the long running immutable calculation. And we can always run the different data points between different data versions, so that we can see the complete history of the data, and it was really important for our historical workflows. So on right hand side, as you can see, I'm just showing you the examples. On the top, it is showing the time series storage where I'm assigning two timestamp. One is on the row level, other one is at column level, and below I'm showing the structural data where the two timestamp is basically stored. So on the first timestamp, I'm showing that, okay, well 2 was not attached to battery 1, but after some time on 13th October, after one day, the well 2 is attached to the battery 1. So I always wanted to store the history of data, and how we achieved this, we basically built bitemporal storage. And just to give you one example, okay, so we are basically we started with a cloud native version of it, but slowly we moved towards a cloud agnostic one. So our first version was created using Bigtable as a storage. So on the top, you are basically seeing the actual Bigtable schema, and bottom for the structural storage, we use another database that's called Datomic. So Datomic is basically by default provides a feature to run a temporal queries, because it basically stores the version time and the transaction time. So consumption workflows. Okay, now our data is stored. We have everything. Now we want to run a robust model so that we can create our consumption. So our consumption workflows are basically interested in looking for the entities and associate properties, what I explained earlier, using the same canonical model. I want to traverse that bitemporal graph so that I can know, okay, if even I need to go multiple level down and find, okay, my pressure is coming from some flow point location under certain well. So I can do that traversing as well. I'm also interested in doing the lot of calculation on the time series data, which is basically aggregation, consuming, and write back. I want to apply the data quality attribute, and all this data is basically feed into some calculation engine, so that this calculation engine is basically running in the background and giving some recommendation and insight to production engineer, okay, and helping them to understand why their oil production is low or why their forecasting is not matching. So all this data is basically helping to run this consumption and workflow. I would like to give Some example like I'm showing here some advanced calculation like validity and source selection. So validity means now we stored all data, all time series data. I want to see if there is a gap in my data, so how much tolerance of this data gap I can have in my workflows. So this calculation is basically, let's say, when I'm feeding this data to that calculation engine and that calculation engine sees some gap, so it basically a backfill to some status code, so that petroleum engineer understand, okay, I have some bad status code or some unavailable status code. So I mean, it sounds simple, but it's a difficult problem to solve, because just imagine someone is seeing last 8 years of second base frequency data. So I always need to find the last known good data point, so that I know, okay, until that point I need to backfill. So this data point could be maybe 1 month ago, or it could be 25 years ago as well. Also, I want to know, okay, I want to merge the different data streams from different data source. For example, any single oil field, if there is some edge device installed and someone is also streaming data from mobile by capturing some image or anything. So, but it is possible that both are sending the same kind of a stream. So I need some way to know, okay, these are same kind of data. So I need to deduplicate it and I want to merge it to the single stream. Other calculations are like, okay, uh, there could be a Monte Carlo simulation, there could be a joining of time series, it could be more than two time series. So overall we created around 1500 time series calculation, what we are feeding it to generate these insights. And yeah, I would like to give some interesting numbers. So this application is basically deployed around the globe, mostly for the oil and gas company in South America, in Southeast Asia, and Middle East. It is managing more than 20,000 oil wells. We have 1500 plus time series calculation. So I would like to give you some numbers for from one client. That client has 7,500 oil well. The typical hierarchy was starting from company, some levels, then field, then well, and number of entities around 30,000. Total relationship we served 60,000, and properties are 1.5 billion. This client has the data streaming for 25 years. So the typical calculation shows we ingested on 14 billion data points. And yeah, these are other numbers like the achievements. I mean, we able to achieve the 98% time saving, 88% cost saving, 80% reduction of the data preparation time. We able to achieve the well uptime as well. And the typical tech stack, I would like to talk. Okay, this is purely a microservice based architecture. We have 40 plus microservices. We are running over two Kubernetes cluster, and 90% services are written in Scala. Few services are written in Go and Python. And we are using Akka a lot. Akka is an actor based framework. And yeah, everything is because we started with the cloud native, but still our future goal was cloud agnostic. So we by default started using Kubernetes. So we are using Kubernetes since 2015. I mean, it's very early days. And for storage, we are using Redis, Postgres, Datomic, and Bigtable. So yeah, I think so. That's all I have, and I'm open for any question.